different properties about them. I'm going to be sharing my screen here in just a second. I don't know what was going on with Teams and the technology this morning, but I finally did get it working. So I'll be sending out the link to this video. So let me share my screen. Okay, so just the objectives, a few objectives that we'll look at here in this section, looking at the domain of rational functions, using arrow notation, finding and identifying vertical and horizontal asymptotes, looking at transformations on the graphs of rational functions. So a rational function is just a quotient of polynomial functions. That means that the rational function can be expressed as some polynomial p of x over some polynomial q of x. The domain of a rational function will be the set of all real numbers except for the values of x that will make that denominator 0, because we do know that division by 0 is undefined. So we will have to exclude those values that make 0 in the denominator. We will have to exclude those from our domain. So that's what we'll begin looking at a few problems where we're identifying the domain. Here's one. You've got x squared minus 25 over x minus 5. The rational function does contain division, okay? And because division by 0 is undefined, we have to exclude from the domain the values of x that will make that denominator 0. So therefore, the domain of f consists of all real numbers except for 5. When we take the x minus 5 and we place it equal to 0, then we solve for x. We have to exclude x equals 5 from our domain. So to show that, we have here, again, the domain of f consists of all real numbers except for 5. So here we have set builder notation or interval notation. Now, in any other class that is not using Pearson, you would probably have the choice. If it was just a paper exam or a paper homework, any assignments that you do on paper that's manually graded by the instructor, we wouldn't care too much about which notation you use. But Pearson, I believe, is really set up using interval notation. So I need you to get in the mind frame of using interval notation, okay? And we've been doing that so far. So I just want to kind of stress that still here. Now, if they I'm going to look at a few examples and see if they don't specify, then you may have more of an option. But we'll see when we get to the homework what the option is, or if there is a set way that they want that the computer will grade. So looking at it, yeah, it looks like it's interval notation. So yeah. All right, so interval notation right here. Let's take a look at that. Now that means 5 has to be excluded from the domain. So what that means is we roll, or we kind of can use a number line. I looked at this before with you guys, where we create a number line that extends from negative infinity to positive infinity. And then you have, for example, a hole in the graph in the number line at 5. So you're chopping the number line up into two parts, basically, from negative infinity to 5. And we do use parentheses to show that it's up to 5, but not including 5. And then we use a parentheses here at negative infinity as well, because we don't know what negative infinity actually is. So therefore, if you don't know what it is, you can't actually reach it, okay? So we use parentheses. And then we use the union to represent or. So negative infinity to 5 or 5 to infinity. Okay. Again, using a parentheses at 5 because it's up to 5 but not including it. And then up to infinity, but we don't reach infinity because we don't know what infinity is. Okay. Here's another example in the notes. And remember, y'all have these notes. Okay. This one has x squared minus 25 in the bottom here. So we would have to solve this It's a difference of two squares, basically. So you can solve this using the square root property. Take 25 to the other side, and that leaves you with x squared equals 25, and therefore x would equal plus or minus 5. Because when you take the square root, remember you had to introduce the plus or the minus. So that means the domain of this function g would be all real numbers except for -5 and 5. And that as well using interval notation. Okay, so we're chopping the number line up here as well, from -infinity to infinity, excluding -5 and 5 from the domain. So -infinity to -5, or -5 to 5, or 5 to infinity. And we're going to look at an example at this point now. So I'm going to minimize that for a little bit and pull up my document camera. Okay, come on now. There we go. All right, let's take a look at this. So we've got, let me scoot this up a bit and try to zoom in here some. So on that first example there, it says find the domain. So you've got 5x over x minus 15. So I just want to show you one of these because I just want to show you how we, chop up the number line. And then on this one, we have, again, finding the domain. This one is negative 8x squared over x minus 2 times x plus 4. I'm sorry, x minus 2 and x plus 4 on the bottom here, whereas you just have x minus 15 here. So remember, we have to exclude values from domain that will make your numerator, that will make your denominator 0. So the x minus 15, we place that equal to 0 and we solve, and we just get x equals 15. So that is the value that must be excluded from our domain. So if I look at the number line, it runs from -infinity to +infinity, okay? And I'll have 15, let's say somewhere here in the middle, and I have a hole at 15 because 15 is not included. So my domain would run from -infinity to 15, parentheses, and then the union sign representing or, 15 to +infinity. Okay? We're going to do the same thing with number 2, two values this time, placing both of those equal to 0, or first starting off with their product, place equal to 0, and breaking each one apart and placing them equal to 0 individually. So x plus 2, adding 2 to both sides gives us x equals 2, and subtracting 4 from both sides gives us x equals a -4. So those two values will be excluded from our domain on this one, from -infinity to +infinity. We'd have -4, a hole there, and then +2, a hole there. So our domain with -4 and 2 restricted from it, be -infinity to -4, because I would reach -4 first, or -4 to 2, because you have to include the values between them as well, or 2 to infinity. Okay? So hopefully you don't find that too bad. Okay? Let's go back to our our PowerPoint, my bad, I'm sorry. Go back to our PowerPoint, our notes, and let's take a look at a few other things here. So the next thing we'll mention, let me scoot this up here. So the next thing we'll mention is vertical asymptotes. Okay. So definition of a vertical asymptote. This is the line x equals a, and a is a value that's going to actually give you 0 in that denominator. It is, and we just take it and write it as an equation, x equals a, is a vertical asymptote of the graph of a function f if f of x increases without bound as x approaches a, or if it decreases without bound as f approaches a. So either direction. Let's take a look at that first graph here again. So as x approaches a from the right, that little plus there in the upper right-hand corner of a means approaching it from the right side of it. So here's your function. As we get closer and closer to a from the right side, the function is headed upwards towards positive infinity. Here, as we get closer and closer to a from the left side, you'll notice the little negative sign or the little minus sign there. So as x approaches a from the left, then the function is also here approaching positive infinity. The other direction, here, it could decrease without bound as well. As x gets closer and closer to a from the right, if the function is decreasing without bound, you can see here f of x is approaching negative infinity as x gets closer and closer to a from the right-hand side, and f of x is again approaching negative infinity as x gets closer and closer to a from the left side. So when locating vertical asymptotes, if you've got a rational function, and if p of x and q of x, the numerator and the denominator, have no common factors, then the zeros, the values that you solve for q, the values of q that you've actually placed q equal to 0 and solve for, the zeros, then that can actually, the value a, if it's a 0 of this denominator, then writing it as an equation, it becomes a vertical asymptote of the graph. Let's take a look at that. Oh, first off, notice that it said first have no common factors, because sometimes you'll have a rational function where a term on the top can cancel with the term or a factor on the bottom. But let's take a look at a few. So this example says find the vertical asymptotes, if any, of the graph of the rational function. Here's your function, f of x equals x over x squared minus 1. So when you look at the numerator and the denominator, the first thing I need you to notice is that you can't do any simplification. They have nothing in common. Okay, you can't factor or cancel out a common factor from top and bottom. Why? Because this x squared minus 1 is one whole expression. So you can't just say, well, cancel x with an x. You can't do that, okay? What you'd have to do is factor this denominator and then see if one of its factors could cancel with a factor on top. But that won't happen either. This is a difference of two squares, and so there's no common factors here with that. So because there are no common factors in the numerator or denominator, then we go straight into looking at the denominator and trying to solve it for 0, trying to solve it by placing it equal to 0. So x squared minus 1 equals 0. We take the 1 over to the right-hand side. That gives us x squared equals 1. And then we take the square root, applying the square root property. That gives us x equals plus or minus 1. So the zeros of the denominator, the solutions of the denominator, because remember 0 is just another name for solution, they are -1 and +1. Thus, when you write those as equations, you're forming the lines x equals -1 and x equals +1. They are the vertical asymptotes for that graph. And I want to illustrate this. I'm going to show you this on the graph. Here it is. Now, if we graph this on our calculator, of course, we won't see these broken dotted lines. They are the vertical asymptotes. And you'll see how the function has to, of course, get kind of choppy because of it having breaks in the graph. So you've got part of the graph here on the left side of this asymptote, and then you got some of the graph here in the middle or in between the two asymptotes, and then you got part of the graph here to the right of this second asymptote. So unfortunately, with rational functions, they are not continuous, okay? They have breaks in the graph because of the asymptotes. But this branch and this branch here in the middle, and then this one all together make up the whole graph of that rational function, okay? Let's look at this one. It says find the vertical asymptotes, if any, of the graph of the rational function. So here it says you've got h of x equals x minus 1 over x squared plus 1. So the first thing you would try to do is see if you can factor the denominator in order to try to cancel out a common factor. But x squared plus 1 is not factorable, okay? It's not factorable. And also, so there's nothing you can cancel out with top and bottom. And then also, when you do try to solve that denominator to find the zeros, the real zeros, there aren't any, because this ends up being x squared equals -1. And then when you try to take the square root of a negative, you would get an imaginary number. So there are no real solutions to this denominator. So therefore, there are no vertical asymptotes. In other words, the graph of this function, because you can always look at it on your calculator, will be continuous. There are no breaks in the graph. Okay? All right, so before we look at horizontal asymptote, let's look at a few problems, and then we'll come back to that. All right, so let's look at number 3 and number 4. We're looking at the graph of some rational functions, and we're asked to determine what the function is doing as x approaches a particular asymptote, okay? So here it says as x approaches to from the left. So that little sign right there, that means we're approaching it from the left. Okay, so when I look at -2, let's find it. Here's -2. Here's the asymptote -2. As x is approaching it from the left, f of x is increasing without bound towards positive infinity. It's going up. So as we get closer and closer to -2 from the left, that means I'm coming this way from the left. If it said from the right, then I would be coming from here, from this direction. But from the left, the function is increasing without bound towards positive infinity. Okay? Let's look at this one. A similar graph, or yeah, very similar, maybe the same graph. I don't know. So here, as x approaches 2, no, this is a different graph. As x approaches 2 from the left, okay, so +2, here's +2. So this is your +2 asymptote, x equals 2. As x approaches it from the left, so here we are getting closer and closer. I'm on the left side of it because here's the asymptote. Here I am on the function from the left. Then as we get closer and closer to 2, the function is increasing without bound. So it's headed towards positive infinity. Increasing without bound means headed towards positive infinity. Decreasing without bound would mean it's headed towards negative infinity. Okay. Let's look at this one. It says use the graph of the rational function. Again, same directions. As x approaches negative infinity, okay? So this is different. So as x approaches negative infinity, so here's the x-axis. Remember, x is horizontal. So headed towards negative infinity means we're going towards the left, okay? So as x approaches negative infinity, as we move towards the left, the function here's the function that we're able to really look at as we get closer and closer, or more and more towards negative infinity to the left, the function is flattening out. It's getting closer and closer to the x-axis, which means that it's approaching 0. So when you're dealing with these graphs, they will, or they can head or increase without bound or decrease without bound. And then they can also flatten out, level out, which is actually something called a horizontal asymptote, which we're going to look at in a minute. But they actually can flatten out as well and get closer and closer to that x-axis or some horizontal line. In this case, it is the x-axis, which means the function is approaching 0 as x heads towards negative infinity. Okay? Let's see what else we have here. All right, good. So the next couple of problems, we're asked to find the vertical asymptotes. So that's perfect. So we looked at the graphs that showed us an image of, how to describe what the function is doing as we approach vertical asymptotes. Let's now look at finding vertical asymptotes, seeing if we have any. So number 6, find the vertical asymptotes, if any, and the values of x corresponding to holes, if any, of the graph of the rational function. So what you always want to do first is see if the function can be factored if top or bottom can be factored. That way you can see if there's a common factor that can be canceled out from top and bottom. But in this case, x cannot be factored. It's just a linear x. And x minus 8 is a binomial factor. Nothing can be done there either. So there are no common factors. So no common factors on top and bottom. So that means we go straight into looking at that denominator and setting it equal to 0 to solve. Okay, so x minus 8, we would say plus 8. Okay, and that gives us x equals a positive 8. That is the solution, the 0 to that denominator. So that is the vertical asymptote. So there is one vertical asymptote. There are no holes. I will explain when we see one where we've got a hole in the graph. I think number 8 is going to be one like that. Basically, what it is, it becomes a hole, or it is a hole when originally a particular value made you have 0 in the denominator, but that factor could cancel out with top and bottom. So we'll look at that in just a second, okay? So we've got x equals 8. That is a vertical asymptote. There are no holes. So the vertical asymptote is x equals 8. You're going to express that as an equation, just like we have there. And there are no holes. Okay. Number 7, find the vertical asymptotes, if any. You've got x plus 3 over x times x minus 1. So top and bottom, you can't factor. They're already in their factored form, or they're in their simplest form. And there's no factors that you can cancel out here either, okay? So that means we take the denominator and we place it equal to 0 and we solve. So I'm going to break each of those factors apart and place them equal to 0 individually. X equals 0 and x minus 1 equals 0. So one of your vertical asymptotes is just x equals 0, and the other one is x equals 1. So you have two vertical asymptotes. And let me see, they want us to, yes, they do want us to express them as equations. It says it right there, type as an equation. So there are two vertical asymptotes, and there are no holes in the graph. So with number 7, we select C, x equals 0, comma, x equals 1. There are no holes. Okay? Now let's look at number 8. It says find the vertical asymptotes, if any, and the value of x corresponding to holes, if any. So we've got x squared minus 144 over x minus 12. Okay? Now, this one, I want to see if it's factorable on the top, because I may have a factor on top that will cancel with a factor on the bottom. And if so, that means that is not a vertical asymptote. Instead, it would become a hole in the graph. Okay, so let's take a look at that. So x squared minus 144, that is a difference of two squares. So I'm going to factor that as x plus 12 times x minus 12. How did I know to do that? Because I'm looking for factors of 144, okay? And it's a perfect square, so 12. And then factors of x squared, that's a perfect square, so x. And because I have a minus here for that constant, I have different signs. So x plus 12, x minus 12, because the inner and outer products cancel out. That's why you see no middle term. Positive 12x and negative 12x, you don't have a middle term. And then on the bottom, you still have the x minus 12. So when we factor this, take a look now. X minus 12 cancels with x minus 12. So technically, that original function could be simplified to give you x plus 12. So because it could be simplified, which would allow you to remove the denominator altogether in this case, that denominator, that value, x minus 12 equals 0, the original denominator, it is now a hole in the graph. X equals 12 is a hole in the graph. So it's kind of basically a removable discontinuity if you think of it. If you think of it like that. A vertical asymptote is a fixed discontinuity, but a hole is basically where the original function had a broken spot or had a discontinuity in it, but it could be removed. Okay, so we express that as a hole. So we have no vertical asymptotes, but there is a hole in the graph corresponding to x equals 12. Okay? Questions on that? Well, I'm sorry, y'all can't ask me right now. There's a video. All right, let's keep on rolling. Let's keep on moving here. Okay, so I'm going to go back here and see what my lecture notes say right now, where that bring us to. And it should bring us now to a horizontal asymptote. So horizontal asymptote. So remember, vertical asymptote is a broken something vertical, a line vertical, where the function approaches it from the left or right, but it's a break in the graph. A horizontal asymptote is basically where you're kind of capping the graph, where it's a value that the function will approach, but it won't ever reach it. And it's horizontal, so it's a horizontal line basically. So the line y equals b. So notice we changed the variable. Remember when it was vertical, it was crossing the x-axis. It was intersecting the x-axis. So we called that line for the vertical asymptote x equals a, where a was some number. Well, in this case, a horizontal asymptote crosses the y-axis. So notice that we use y equals some number b for it. So the line y equals b is a horizontal asymptote of the graph of a function of f if f of x approaches that number b as x increases or decreases without bound. So as x approaches positive infinity and the function approaches that value b, then that means y equals b is a horizontal asymptote. And then here it's approaching it as well as approaching it from above it. Here it's approaching from below. And even here, where it crossed over here, the asymptote, but then it flatlined to approach it this way. So both of these, or all three of these graphs, we're examining where x is approaching positive infinity, that f of x is approaching that horizontal asymptote b. Even if it was the other direction, it could be similar. As x approached negative infinity, the function could approach b, okay? So either direction. So how do we find horizontal asymptotes? There, this time, we have three different cases that you kind of got to pay attention to that will determine or help you determine if you have a horizontal asymptote and what it is, okay? So it says, let f be the rational function given by, and this is just where you have some polynomial function on top divided by some polynomial function on the bottom, okay? Excuse me. So one of the first things that you have to do in order to determine if we have horizontal asymptotes is identify the degree of the numerator and the degree of the denominator. When I say degree, I mean the highest exponent. So the degree of the top and the degree of the bottom. If the degree of the top is less than the degree of the bottom, so if the highest exponent is less than on top than it is on bottom, then the x-axis, or simply the equation y equals 0, is the horizontal asymptote. So that means the function, as x increases without bound, the function will approach 0. Y will equal 0, or the function f of x will approach 0. If they have the same degree, if n equals m, then that means the line of the leading coefficients, a over b, will be the horizontal asymptote. And then finally, if the degree of the top is greater than the degree of the bottom, there is no horizontal asymptote. Okay? So let's look at one of these here. This example says find the horizontal asymptote, if any, of the graph of the rational function. So take a look. You've got 9x squared over 3x squared plus 1. So to find the horizontal asymptote, take a look at the degree of both the top and the bottom. They have the same degree. The degree of the numerator is 2, and it is equal to the degree of the denominator, which is 2 as well. So therefore, we examine the leading coefficients. They are 9 and 3. And we write our horizontal asymptote to be equal to, or to be represented by y equals 9 over 3, which then simplifies to just y equals 3. And here would be a graph of that. So we could look at this graph in the calculator, and you would see that it's flattening out as the function increases without bound, as x increases without bound towards positive infinity, the function is approaching 3. And then here, again, as x decreases or approaches negative infinity, then the function is also approaching 3. Take a look at this one. Find the horizontal asymptote if any of the graph. Your function is 9x over 3x squared plus 1. So this time, the degree of the numerator is 1, and the degree of the denominator is 2. So the graph of G would have to be just the line y equals 0, because the degree of the top is less than the degree of the bottom. And according to the rule, if we go back here, according to the rule, if n is less than m, then your horizontal asymptote is just the x-axis, or just y equals 0. Okay? All right. Let's take a look at an example here. Number 9. So here I've got 11x over 5x squared plus 2. So to get the horizontal asymptote, I want you to notice that the degree of the top is 1 and the degree of the top is 2. So n is less than m. So therefore, the horizontal asymptote is y equals 0. That is the rule. So the horizontal asymptote, we select A, y equals 0. Okay? Number 10, you've got the degree of the top is 2, and the degree of the bottom is also 2. So n equals m in this case. So your horizontal asymptote will be the line y equals 20 over 5, the leading coefficient of the top over the leading coefficient of the bottom, which then becomes y equals 4. Okay? And then number 11, the degree of the top is 3 and the degree of the bottom is 2. So n is greater than m. So there is no horizontal asymptote. Okay? No horizontal asymptote. All right. And then finally, the last few problems, I believe, are related to a 7-step strategy for graphing. So we'll look at one or two of these. And then that's really the end of this section, which would then be the end of this module. So before we do look at that problem, let me go back to my PowerPoint, my notes here. So you do want to have maybe just an idea of what the general rational function would look like. And then we've got some different properties that we may have to think about when we are actually trying to graph. And of course, you have your calculator as well. So here is one. Let's take a look at this. Basic reciprocal functions. So in order for us to look at the graph, I want you to understand that sometimes you have a property of symmetry. You want to see if symmetry applies. So, excuse me, I'm sorry. So these are two basic reciprocal functions, rational functions. They're rational, and they're the reciprocal functions. Um, Here is 1 over x. This one is an odd function, because if you were to replace x with a negative x, you would get the opposite of every point. You would get opposite of f of x. So it has origin symmetry when that's the case. And then this function, 1 over x squared, it's an even function, because if you were to replace x with negative x, then you would still get the original f of x. And it has y-axis symmetry, because you could basically fold it along the y-axis, and the left side of the graph would mirror or lay on top of the right side. This one has origin symmetry. If you were to fold it horizontally and vertically, then it would lay this leg of the graph, this branch would lay on this branch, origin symmetry. So we can use transformations on these two basic rational functions, because these are the two basic rational functions, just 1 over x and 1 over x squared. We can use those to help us kind of look at the graphs. But you will not be graphing by hand, and you won't really have to do transformations either, but you will have a 7-step strategy for graphing that we'll look at. So let me get to that. It says the following strategy can be used to graph f of x equals p of x over q of x, where p and q are polynomial functions with no common factors. So the first thing you want to do is determine if the function has symmetry. And remember, we're looking for either y-axis symmetry or origin symmetry when it comes to these basic rational functions. If it has y-axis symmetry, then that means if you were to replace negative x with, if you were to replace x with negative x in the original function, and you get the original function back, then that function has y-axis symmetry. If you were to replace x with negative x in the function, and you get the opposite of f of x, okay, then that means you have origin symmetry. So that's one of the first things we'll do. Then we'll also look at finding the y-intercept, if there is one. Sometimes there isn't. And we'll do that by evaluating the function at 0. Remember, the y-intercept is when you let x be 0. So we would evaluate the function by letting x be 0, f at 0. We'll find the x-intercepts. That would be where we take the top p of x, we take the top equation, the numerator, and we place it equal to 0 to solve. Okay, that will give us our x-intercepts. Then we'll look and see if we have vertical asymptotes. That's where we solve the denominator by placing it equal to 0. Okay. Then we'll look at finding horizontal asymptotes. So basically, we're kind of compiling all the different steps as far as functions in general, and then specific parts or key factors for rational functions. Because, symmetry, y-axis symmetry and origin symmetry, we talked about even before this section with other functions. So we're going to use that strategy to help us graph. We'll find the x-intercepts by solving. We'll find the y-intercept by evaluating the function at 0. So these rules or these steps are steps that we're familiar with. We're just bringing them all together. Now, the new steps were new to this particular section will be step number 4, where we identify or find vertical asymptotes, and step number 5, where we find and identify horizontal asymptotes. And then we will plot at least one point between and beyond each x-intercept and vertical asymptote. Okay, we'll look at that. And then we'll use this information that we obtained previously to graph the function between and beyond the vertical asymptotes. We'll use that information to graph. So let's take a look at an example here. Let me just kind of run through this one in the notes here, and then we'll look at the homework. So this one says graphing a rational function. You've got f of x equals 3x minus 3 over x minus 2. So the first step is to see if we've got symmetry. So we're evaluating the function at negative x. So wherever we had x, we're replacing it with a negative x. So 3x minus 3 becomes 3 times negative x minus 3, which is just a negative 3x minus 3. And then on bottom, x minus 2 becomes a negative x minus 2. But because that constant 3 and that constant 2 didn't change, even though the first term on top and the first term on bottom did, because the second terms, those constants, did not change sign, then it's neither the original, because it's not giving us that right back, and neither is it the opposite. Okay, so the graph has neither y-axis nor origin symmetry. Okay, so that's one of the first things we look at. Then we find the y-intercept. We do that by evaluating the function at 0, replacing 0 into the function where we saw x. And then we find then we find the x-intercepts by taking the numerator. Remember, the numerator was 3x minus 3. Taking that numerator and setting it equal to 0 to solve. So 3x equals 3. And then solving that, dividing by 3, x equals 1. All right, vertical asymptotes is where we take the denominator and we place it equal to 0 to solve. Okay, and that denominator was x minus 2, so we solve that by placing it equal to 0. So x equals 2 is a vertical asymptote. The horizontal asymptote is where we look at the degree of the top and the degree of the bottom. They have the same degree, so therefore the horizontal asymptote is just going to be a equation of where y equals the leading term, the leading coefficient from the top, divided by the leading coefficient of the bottom. So just y equals 3. 3 over 1, y equals 3. And then we plot some points, and they're going to give us some values that they want us to actually plot to help us actually see the graph. But you started off with just kind of putting in the vertical asymptote, putting in the y-intercept, putting in the x-intercept, and then plotting some points at some given values that they want us to find. We evaluate the function at those particular given points of values for x. And that's in a table, and you'll see that in the homework that they provided us with a little table, and they basically give us some values for x that they want us to find or evaluate the function at. And then those give you some points that you'll place on the graph, such as these, so that you can actually see a decent image of the graph. And of course, we're going to look at the calculator anyway, but I wanted you to see how that would be done if you were taking the points from the table along with the y-intercept, along with the x-intercept, the vertical asymptote, and the horizontal asymptote. Putting everything together, it gives us a decent image. Okay? So let's look at some homework. Let's look at one. Pretty straightforward for the most part, though. But let's take a look at which one I want to look at. We can look at number 13. Let's do number 13. So we've got here f of x equals 7 over x squared plus 2x minus 15. So the first thing we do is see if we've got symmetry. So I'm going to find f at negative x and see what that gives me. So I've got 7 on the top, and then on bottom, I'm going to take the x and replace it with negative x. So I've got negative x squared plus 2 times negative x minus 15. Okay? So that gives me still 7 on top. That gives me x squared again right there, because that negative becomes positive. And right here, this becomes a minus 2x, and then I still have minus 15. So this is not the same anymore, okay? That middle term switched. So this function is not even. It doesn't have y-axis symmetry, and neither does it have origin symmetry, because this is not the opposite of that. In order for this to be the opposite, every sign or the whole thing would have different signs. So neither y-axis symmetry nor origin symmetry. In order for it to have origin symmetry, every term would have to have the opposite sign of what it was originally. Okay. All right, then we get to where we want to find the y-intercept. That's where we find f at 0, or we evaluate f at 0. So 7 over 0 squared plus 2 times 0 minus 15. What does that give us? Let's see. So we have 7 on top, 0 plus 0 minus 15. So negative 15 on bottom, that's just a negative 7 over 15. So our y-intercept is, and they say to just type it as an integer. They don't want it as an equation. So it's just negative 7 over 15. Okay. The next thing is the x-intercept. It looks like we don't have any x-intercepts, because to get the x-intercepts, we would take the numerator and place it equal to 0 and solve. But that numerator is just a constant 7, and 7 doesn't equal 0. So there are no x-intercepts. So remember, to find the x-intercepts, put this on here, to find x-intercepts, we place the numerator equal to 0 and we solve. But in this case, the numerator was just a constant, so there was nothing to solve. So there are no x-intercepts. Now, to get the vertical asymptotes, this is where we take the denominator and set it equal to 0. So to get the x-intercepts, we take the numerator. To get the vertical asymptotes, we take the denominator. So in this case, our denominator is x squared plus 2x minus 15 equals 0. We take that and place it equal to 0. So I would factor here. I would try to factor here. X squared is x and x. I have different signs here because that's a minus constant term, a negative constant term. So I have different signs, a plus and a minus, or a minus and a plus. It doesn't matter. Now, factors of 15, that will subtract to give me 2. Okay, and I need a positive 2. I'm using 5 and 3, and I need the 5 to be positive because I need a positive 2. So I'm putting the 5 here with the plus and the 3 with the minus. So my vertical asymptotes, therefore, would be x plus 5 equals 0, or x minus 3 equals 0. So x equals a negative 5 and x equals a positive 3. So my vertical asymptotes are equations. X equals negative 5, x equals positive 3. And you write them as equations and just separate them with commas. Okay? Now to find the horizontal asymptote, this is where I examine the degree. So the degree of the numerator is actually is 0 because it's just a constant there. And the degree of the denominator, which would be m, is 2. So the degree of the top is less than the degree of the bottom. N is less than m. So therefore, the horizontal asymptote is just the equation y equals 0. Okay? When the degree of the top is less than the degree of the bottom, the equation y equals 0 is your horizontal asymptote. And then finally, y'all, the last thing we need to look at, we need to find or evaluate the function at these particular values and then choose the graph. I'm going to save you some time even on this. I'm going to go ahead and look at the graph on the calculator. So I'm going to put it in my calculator under y equals. Now, here's the thing, though, okay? I need you to understand something. You have to tell the calculator that this 7 is the numerator. So I'm going to put 7, I'm going to put divided by. I need the calculator to know that this whole thing, this whole expression is the denominator. So I'm going to put parentheses around it. So parentheses x squared plus 2x minus 15. You have to tell it, okay? Because otherwise it won't understand. The calculator is not smart at all. It only knows what you tell it. So we needed to understand that this is the denominator there, that whole thing. There's also another way that you could write it if your calculator has this certain type of format. Let me see here. If I press second zoom, nope, that's not it. I'm trying to remember. No, is it alpha zoom? Yes, and then I go over here to function, I think, or fraction. Oh, fraction. So I pressed alpha zoom and I just arrowed over to frac, and I'm choosing number 1 here, and I should have it in the y equals. Let me try it again. Alpha zoom, and I'm going over here and choosing number 1. There we go. So you do have the option of using that kind of formatting notation to where it's showing you a fraction over a fraction. If your calculator doesn't do that, then just make sure you put this whole thing in parentheses. So x squared plus 2x minus 15. Okay? And then I'm going to hit graph. And you might be wondering, well, I did not fill in the table yet. But remember, your calculator has a table also. So we can pull these numbers from the table on the calculator. But you can see pretty much that we should be able to choose the correct graph, I think. We may have to use a little bit of process of elimination here, but you can definitely tell where you have vertical asymptotes because the graph is discontinuous. It's not continuous here. It's broken. So we got one branch here, and then we got one branch here down below between these two asymptotes. And the asymptotes are not showing on our graph on the calculator, even though you kind of can see them on the graph on the paper here. You can kind of vaguely see a little broken dotted line. Okay, so I'm going to go to the table and fill in these values from the table though. So let's press second graph. And so I now can tell now when I let x be -6, I get, look, 7/9. When I let x be -2, I get -7/15. And also, if you don't use that fraction notation, it may give you decimals here. So if ever you had decimals and you wanted it to look like a fraction, then you should be able to, let's kind of see here. Let's press math, frac is highlighted, press enter. Okay, that won't work like that. Let me go. Trying to see if your calculator is showing you something different, how you can make it show you fractions. It should just show you fractions, especially if you put it in this format here. But this is where you may have to do a little bit by hand if your calculator won't change those values, because it may show them as decimals if it won't change them to fractions for you. But it should. If you have this kind of calculator or if you have the regular 84, it should do exactly what I showed you. So in your y equals, then you press alpha, and you can press alpha y, I think, even to get to it quicker. Alpha y. Yeah. And it'll take you to frac and that form n over d, numerator over denominator. Okay. And then I'm going to go back to that table there. So when I let x be 0, I have -7/15. When I let x be 4, I have 7/9. And then when I let x be 6, I have 7/33. And so then finally, I'm ready to choose the correct graph. I'm going to go back to graph. And using process of elimination here, remember you don't see the full on graph, okay? I just see part of it because I've got a 10 by 10 window, I think, which is what they have as well. So process of elimination, I know I'm going to eliminate C because I don't have a middle branch here up here. Mine is below. So it's not C. And neither is it D because this branch right here is supposed to be up, not below. And then this one is supposed to be down here. So it's not D either. So let's look at A and B. And actually, it should be pretty obvious that it has to A when you think about it, because look, your branches, your horizontal asymptote is y equals 0. It's not up here. Because you see how the branches are flattening out up here at some invisible broken line here? But down here, they're flattening out, getting closer to 0 because that is where your actual horizontal asymptote is. So it's A. Okay? Process of elimination. So hopefully this video allows you to complete 2.3 now. Don't forget, y'all, lecture, I pretty much kind of go over, expand on what the lecture videos kind of first introduced to you. So make sure you're watching your lecture videos. I try to just go over examples and talk just briefly, keeping my talking to a little less and showing more examples. So do please finish module 2 and take that exam because we're approaching the midterm very soon, which we'll talk about in class next week. And that's all I have for you. Y'all have a wonderful day.